All right, sorry that I didn't have notes to give you guys on this. Um, Suppose that your company, and this kind of goes along, we've been going with this theme, produces 1 million computer chips, and the probability of a defective chip is 0.02. What's the probability that no more than 19,800 chips are defective? So notice all of a sudden I've got some really large numbers. So if we take a look at this situation, notice we have two outcomes. The chips are either defective or not defective. The probability of success, p equals 0.02, which is our defective chip, is the same for each trial. The question of independence, we do have a finite population. It is very large, but we have a finite population. So we need to assume that the company has produced over 10 million chips. I don't know if that's reasonable or not, but we're going with it on this because I want to show you something that we needed to have some large numbers for. We do have a set number of trials, which is 1 million. So that makes it binomial. So we have a binomial model. N is 1 million, P is 0.02. Remember that this is the notation for a binomial model. So if we were to go ahead and say, all right, well then let's look at this. We want the probability that no more than 19,800 chips are defective. So I'm looking at this situation. So then I'm going to use Binomial Cdf. So if I grab my calculator to try this. So second distribution, I'm going to do the up arrow because it's a little shorter. Binomial Cdf. My trials are 1 million. My probability of success is 0.02. My x value is 19,800. And notice that what I wrote here, binomial CDF, that's kind of what they would put right here. Uh-oh, we got a problem. The problem actually is, since it's a domain error, these numbers are so huge. To do 1 million choose 19,800 and do 1 million factorial, your calculator can't handle that. So we can't do a binomial with because the numbers are too big. So here's our workaround. We can actually use what's called a normal approximation to the binomial. Prior to graphing calculators that easily allowed you to calculate binomial model problems, we would have to do normal approximation frequently, all the time, to do the binomial calculations. So the only thing what has to be true is as long as we have at least 10 successes and at least 10 failures, then we can do the binomial model. So that means we have to check and make sure that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. If we take, for our problem, if we take 1 million, if we take 1 million times 0.02, then we're going to get 20,000, which clearly is greater than or equal to 10. And if you take 1 million times 0.98, then you're going to get 980,000, which again clearly is greater than or equal to 10. So we have no problem here. Obviously we have, these are huge numbers. Had I used some smaller numbers, you'd have been able to do the binomial directly with our calculators, which is fine, but I just wanted to show you an example that you couldn't use the binomial, so you have to use the normal approximation. So we can use a normal model to approximate this binomial, which a normal model, remember, has a mean and a standard deviation. So then the question would be, well, what do you use for the mean and what do you use for the standard deviation? So this is from your yellow sheet. And if you recall that the mean, this is binomial right here. So the mean of a binomial model is n times p. And the standard deviation of the binomial model is the square root of n times p times 1 minus p. I think your textbook uses npq, where q is 1 minus p. So when you see that, that's all that is. So using those, I'm going to use, since the mean mu sub x is n times p, which in our problem is 20,000, sigma sub x, if I calculate that, I get 140. So I'm going to use an approximate normal model, and actually I could have written it like this just so it's n times p, and then the square root of n times p times 1 minus p. So that's what I'm using for my mean and standard deviation of my normal model. It's very important that you recognize that this is approximately normal. Not exactly normal, but approximately normal, and that's a way that you can do that with a little squiggle. I'm looking for the probability that x is less than or equal to 19,800. I'm going to draw a picture. My mean is 20,000. I just counted off 3 standard deviations and I just went to the left, located around where 19,800 might be, and I'm shaded the correct region. This is my work. Since I'm using my calculator and not doing z-scores, this is my work. I need to show that. Then I just do normal CDF. Using your calculator, we can show that. So if I do second distribution, remember that we never use normal PDF, just CDF. So for my lower bound, I want something ridiculously low. When I type it in as -10 to the 99. It will change it to, it changes it. The upper would be 19,800. You kind of can see that from your picture if you're not sure about that. And our mean, 20,000. And our standard deviation, 140. And our calculator can handle this. And if we round to 4 decimal places, I get 0.0766. So that would be the probability. Again, remember that this is an approximation, but it's a good approximation. So on some of the homework problems you might be asked to do a normal approximation to the binomial. You might be asked to do with the exact binomial and then also show with the approximation of the normal to see how close they are. But typically, you won't have to use the normal approximation to the binomial unless you had to. Like this situation that I came up with here, we had to. So hopefully that helps. That should complete all of our instruction from chapter 17. So you will have an assignment to apply this.